Hello, this is regulation of glycolysis, section 16.4, and this is part 2. So we are talking about the regulation of the 3 enzymes of glycolysis and in muscle and in liver. And so glucose is phosphorylated by using ATP as the phosphoryl donor, hexokinase and glucokinase. Glucokinase in the liver, hexokinase in the muscle, regulated differently. So let's continue. Glucose 6-phosphate is changed to fructose 6-phosphate by glucose 6-phosphate isomerase, and then there's another one-way enzyme to make fructose 1,6-bisphosphate, and that enzyme is phosphofructokinase. Phosphofructokinase. I got it backwards. Let me use my eraser. I had it right, and then I changed it. Phosphofructokinase, PFK. When we learn about gluconeogenesis in the next chapter, we're going to find that there's another enzyme that converts fructose 1,6-bisphosphate into fructose 6-phosphate, and that is a different enzyme, so we won't talk about it yet. Okay, so fructose 1,6-bisphosphate is phosphorylated, and it gets changed into 2 different molecules, dihydroxyacetone phosphate, DHAP, and glyceraldehyde 3-phosphate, and that's an aldolase. Now it turns out that there is an interesting alternative to the aldolase, and that is that the fructose 1,6-bisphosphate can be changed into fructose 2,6-bisphosphate by an enzyme called phosphofructokinase 2. Makes 2,6-bisphosphate out of 1,6-bisphosphate. And there's another enzyme that does the back reaction, and we won't talk about that yet. But there's this interesting molecule in your cells, fructose 2,6-bisphosphate, which you may have heard about before. And it turns out that this molecule inhibits PFK. And no, it activates it, sorry. So PFK is activated by fructose 2,6-bisphosphate. And that's in the liver only. Okay, so I kind of jumped ahead to liver, but I thought I'd get this set up. Let's go back to muscle, and let's think about these enzymes in the muscle. So I have to go back to the slideshow here. Regulation of phosphofructokinase in muscle cells. So notice that on the left side we have glycolysis when the muscle cell is at rest, when we're just sitting on the couch, not needing much ATP. And on the right side we have a map of glycolysis during exercise, when the muscles are demanding ATP, and glycolysis needs to be stimulated because it makes 2 ATP. So let's look at rest first. So on the left side, glucose catalyzed by hexokinase to glucose 6-phosphate, and then PFK is the third enzyme, and then way down at the end we've got pyruvate kinase. So hexokinase is inhibited by its immediate product, glucose 6-phosphate. So this is an example of negative feedback inhibition. Oftentimes it's the last reaction in the pathway that comes back and inhibits the first enzyme, but in this case it's the immediate product of that enzyme that inhibits it. So hexokinase has an active site for glucose 6, has a regulatory site for glucose 6-phosphate and inhibits it. Okay, now notice that glucose 6-phosphate to the left can be used to make glycogen. Glycogen is simply polyglucose. It's just a storage form. It's an important storage form of glucose that your muscles can make. Your muscles and liver can make glycogen to store glucose. And so one of the fates of glucose 6-phosphate is to continue down glycolysis to pyruvate, but a second fate of glucose 6-phosphate is to be made into glycogen to store glucose. So hexokinase is not the committed step. The carbons of glucose 6-phosphate have two different fates. When we get to phosphofructokinase, though, that is the committed step, and any fructose 6-phosphate that binds to phosphofructokinase will be phosphorylated and end up down the pathway at pyruvate. So phosphofructokinase is the committed step, and therefore it's the main regulatory enzyme of glycolysis. Now, your muscles cells need ATP, and so glycolysis is regulated by the energy charge. In other words, the ratio of ATP to AMP. AMP is the signal for low energy, ATP is the signal for high energy. So if we have a high energy charge, that means we have a lot of ATP, and we don't need glycolysis to continue in the muscles because we already have plenty of ATP. We don't want to waste the glucose. We need to save it for when we do need it. So ATP actually has a binding site on phosphofructokinase at the regulatory site, where when ATP binds to the phosphofructokinase, it slows the enzyme down, so that slows glycolysis down. Now remember that kinases use ATP, so ATP is not only a regulatory molecule, but it's actually the substrate of PFK. So ATP binds in the substrate, in the active site of the enzyme. As it is the substrate, it binds in the active site of the enzyme, and it is a regulatory molecule, and it binds in the regulatory site. So if we go back and look at, here's a PFK, ATP binds in the allosteric sites and in the catalytic sites. So that's very interesting. And we'll look at the reaction velocity for PFK here in a moment. Okay, AMP is a signal for low energy. So when there's hardly any ATP in the cell, the muscle cell says, hey, we need to have an ample supply of ATP. We need to speed up glycolysis. So if the energy charge is low, PFK is actually sped up. And the way it works is AMP kicks ATP out of the regulatory site, and therefore ATP is not slowing the enzyme down, and when AMP is in there, the enzyme can go full speed. Pyruvate kinase also has a regulatory site for ATP, and ATP inhibits pyruvate kinase. Now let's look at the regulation of the same enzyme in muscle cells when the energy charge is low, because the ATP is being used up because the muscles are being used. This is during exercise. So hexokinase, if the glucose 6-phosphate is being used up, it's running down, phosphofructokinase is going fast to make some ATP further down the pathway, then there's not much glucose 6-phosphate, so it's not inhibiting hexokinase. We will have a lot of AMP in the cell, so that will activate phosphofructokinase, and it turns out that pyruvate kinase is stimulated by fructose 1,6-bisphosphate. Now, why does this make sense? If phosphofructokinase, the third enzyme, is going fast, it'll be making a lot of fructose 1,6-bisphosphate, and all of the reactions after that will be going, and there'll be a lot of phosphoenolpyruvate, and we want pyruvate kinase to be turned on. So it's a feed-forward activation. It's a feed-forward stimulation where as soon as PFK starts going fast and making product, pyruvate kinase will be induced to speed up also. So all three enzymes will be going fast, making more ATP. Okay, So let's review PFK, the reaction of PFK. Notice that fructose 6-phosphate and ATP are, it seems like this, oh, it's not wrong in your book. They fixed this error. I just noticed that it looks like ATP is a product of phosphofructokinase, but it's not. It's a reactant. So my slide is wrong, but in your book, I think it's corrected, and it's probably right in your book. I hope. Okay. Yeah, so let's review that reaction. And I forgot to set my alarm, and I think I better review it in my next part 3.